Welcome back to Basic Electronics. In this lecture, we will continue with sinusoidal oscillators and look at how the output amplitude can be controlled using a gain limiting network. After that, we will consider an important limitation of amplifier circuits which we have not addressed so far, and that is frequency response. We will first look at the frequency response of an inverting amplifier for different gain values. We will then explain this frequency response with a realistic model of the op amp. Okay, let us get started.
Okay, so here is our complete implementation, and let us first relate the implementation with our block diagram. What is XO in the implementation? That is of course VO. What about XF, which is beta times XO? XF in this case is this current here, not shown, but as we discussed in the last slide, XF in this case is not a voltage but it's a current. What is our A? Our A is not a voltage to voltage gain, but it's a current to voltage gain, and that we found to be equal to minus RF. Alright, now for this beta network, we found that omega 0 would be 1 over square root 3 1 over RC, and that gave us F0 equal to 574 Hertz, and we have already done that calculation previously, just repeating it here. And our RF we found in the last slide should be equal to 12 times R. R here is 10K, so 12 times 10K is 120K, and we make it slightly larger than 120K. So that is how we get this 125K. And that is done, as we mentioned earlier, to make sure that the circuit does oscillate on power up. This is the gain limiter block, and we have seen this circuit earlier, if you recall. Let us see how it works. We have seen that the gain of this amplifier is minus RF. Now when this voltage is small, these diodes are off, and the only resistance then is RF, so the gain is large. When this voltage increases, either in the positive direction or in the negative direction, one of these diodes turns on, and then this net resistance decreases, and that is how the gain decreases as the voltage increases. So that is how gain limiting is achieved. Here is the output voltage obtained by simulation, and the circuit file is specified here. You can try out this simulation as well. And let us check whether it shows the correct frequency. The frequency of oscillation that we expect is F0 equal to 574 Hertz, and that gives us a period T equal to 1 by F0 equal to 1.74 milliseconds. And we see that in 1.74 milliseconds, somewhere here, we do have one cycle, and therefore the result seems to be correct. Now the question that arises is, can we do something about this amplitude? The answer in this case is yes. We can play with these parameters here and use those to change the amplitude of the output voltage, and let us see how that can be done. Here is the gain limiting network that we used in the phase shift oscillator. The values are a little different, but that's not very important. And if you recall, we have seen this circuit earlier with these values 60K, 15K and 20K, and in that situation we had obtained I versus V given by this dark curve here, and dV di, where V is this voltage and I is this current, was given by this curve here. So in this region of the voltage, the resistance is constant, and then on either side it starts dropping because one of these diodes starts conducting. And our gain limiting happens when this resistance falls here. Let us now connect this picture with the amplifier that we saw in the phase shift oscillator in the last slide. And if you recall, the gain was proportional to minus Rf. So when the resistance is high, the gain is high, and when the resistance drops, the gain becomes low. In other words, the gain is constant in this region, and outside it drops, and that is what causes amplitude limiting. Now if we increase the width of this region, then we will also increase the amplitude. So that is the basic idea behind amplitude control here. How can we change the width of this region? There are different ways of doing it. We can change R1 and R1 prime together, or we can change R2 and R2 prime together, or we can change this power supply. Of course, the last option is not very practical because we don't want to change the power supply values. What we have done here in this plot is we have changed R1 and also R1 prime. This is the plot for 15K, the dark one, as we have seen already. The next plot is for 25K. That means this resistance is 25K. This one is also 25K. And the one after that is for 40K. As we change the resistance value, we notice that the breakpoint also shifts. Here is the breakpoint for 15K. For 25K it is here, and for 40K it is here. It can be more clearly seen in this bottom picture. That is the breakpoint for 15K. For 25K it is here, and for 40K it is here. So if we change the resistance from 15K to 40K, what it means is that the amplitude will change from about this much to about that much. And let us check that out now with the help of simulation in the next slide. Let us now look at the simulation results for the phase shift oscillator. The component values here, R and C and RF, are the same as what we had in the last slide. So the frequency of oscillation is expected to be the same, namely 574 Hz, and that corresponds to a time period of 1.74 milliseconds, if you recall. What we have done here is change this resistance, and that means that we also change this resistance, and the output voltage is plotted for 3 different values of the resistance. This waveform corresponds to a resistance of 0.5K, this one to 1K, and this one to 2K, and the amplitude control can be clearly observed. The frequency of oscillation, of course, does not change, and we can check that out. We can identify the peaks, for example this one and this one, see the difference between these two peaks, and that should turn out to be 1.74 milliseconds. And that will be also true about the other waveforms. So we can take the difference between this and that, or that and that, and all of these will turn out to be 1.74 milliseconds. Now one comment about the phase of these waveforms. The phase is different for each of them, but the phase is not particularly relevant here, and we can just ignore it. Let us now revisit the inverting amplifier, which we have seen earlier, and discuss a very important topic which we have not touched upon so far. So here is an inverting amplifier circuit with R1 equal to 1K, and we are going to change R2, consider different values of R2, and that's why we have not specified the value here. As we have seen earlier, the voltage gain for this amplifier is minus R2 by R1, and we expect the gain to be independent of the signal frequency. But that does not happen in real life. A measurement with a real op amp shows that the gain starts reducing at higher frequencies. and let us see how. Here is a plot of the gain in dB versus frequency in hertz, where the frequency is plotted on a log scale, and we consider various values of R2, 5K, 10K, 25K and 50K. Let us look at the R2 equal to 5K curve. What is the gain for this R2? It's R2 by R1, so 5K by 1K or 5. We have to convert that to dB, of course, and that gives us this value here. Now the important point to observe is that the gain is constant for much of this frequency range, all the way up to say 10 kilohertz or a little higher than that. But at some point it starts falling, and this fall is called the roll off of the gain with frequency. What happens if we change R2 from 5K to 10K? The gain doubles and we have a higher gain here, but also the roll off of the gain with frequency starts happening at a lower frequency now. For 5K it happened here, for 10K it's happening here, and for 50K it's happening at an even lower frequency. So that's a very important point to observe, and it has of course important practical implications as well. So if the gain is increased, the gain roll off starts at lower frequencies. And this behavior has to do with the frequency response of the op amp, which we have not considered so far. So let us look at it now. Let us start with the frequency response of the op amp, in particular op amp 741. Here is the gain in dB versus frequency in hertz, and we are plotting the frequency on a log scale going from 0.1 hertz all the way up to 1 megahertz here. So it's 0.1 hertz, 1 hertz, 10 hertz, 100 hertz and so on. Now the ideal response of the op amp 741 would be flat, that is, it would be independent of the frequency. But this is what the real response looks like. It starts dropping off at some frequency here, and then it reduces at the rate of minus 20 dB per decade. And if we join this asymptote with this one, they intersect at about 10 hertz. So what it means is that the gain of the 741 op amp starts falling at rather low frequencies with a cutoff frequency or 3 dB frequency of only 10 hertz. And this may come as a surprise, but this fall off at 10 hertz is not accidental. The 741 op amp and many others in fact are designed with this feature, that is a fall off at a relatively low frequency like 10 hertz, and that is done to ensure that in typical amplifier applications the overall circuit is stable and not oscillatory. In other words, the op amp has been internally compensated for stability. And you will learn more about stability of amplifiers in an advanced analog circuits course. For now, it suffices to know what the op amp 741 frequency response is like, and with that in mind we will now try to understand the frequency response of the inverting amplifier, which we saw in the last slide. The frequency response of the 741 op amp can be represented by this equation here. A of S or j omega equal to A0 divided by 1 plus S by omega C. And it is easy to figure out where this is coming from. This is our frequency response. We have only one corner frequency somewhere here, two asymptotes, that one and that one. And this asymptote has a slope of minus 20 dB per decade. So what it indicates is that there is only one single pole in this entire system, and therefore A of S is equal to A0 by 1 plus S by omega C. A0 is the low frequency gain, which is 100 dB. 100 dB corresponds to 10 raised to 5. So A0 is just a constant equal to 10 raised to 5. and omega c is the cutoff or corner frequency, that is somewhere here, and in hertz it is about 10 hertz. In radians per second it is 2 pi times 10 radians per second. Okay, so here is our a of j omega again, a0, which is a constant, divided by 1 plus j omega by omega c, where omega c is about 2 pi times 10 radians per second. Now let us consider the case where omega is much larger than omega c. So that means we are away from this cutoff frequency, say somewhere here. And in that case, this 1 is small, and we get a of j omega equal to a0 divided by j omega by omega c. And note that this quantity becomes 1, the magnitude of a of j omega becomes 1 when a0 is equal to omega by omega c. That is, when omega becomes equal to a0 times omega c. And this frequency, omega equal to a0 times omega c, is called the unity gain frequency, and it is denoted by omega with a subscript t. And for the 741 op amp, the corresponding frequency in hertz, which is denoted by f with a subscript t, is a0 times fc, where fc is this corner frequency or the 3 dB frequency. That is 10 raised to 5 times 10. A0 is 10 raised to 5 and fc is 10 hertz. So that ft for the 741 op amp turns out to be 10 raised to 6 hertz. So that is our unity gain frequency for the 741 op amp. So fc is marked over here in the plot, and ft is 10 raised to 6 hertz. Alright, now let us see how the frequency response of the 741 op amp affects the gain of an inverting amplifier. Here is our inverting amplifier, and we want to understand its frequency response now, which we have seen earlier. First, what we will do is replace the op amp with its equivalent circuit model consisting of the input resistance Ri, the output resistance Ro, and this gain element. We will assume that the input resistance is very large, so that becomes an open circuit. The output resistance is very small, so that is a short circuit, and that gives us this equivalent circuit over here. Open circuit here and a short circuit here. And now what we want to do is to get VO by Vs as a function of frequency, and that frequency dependence of course will come from the frequency dependence of AV of the op amp, which is shown over here as AV of S. Okay, so let us start with the voltage at this node with respect to ground, and we can obtain that by superposition. We have Vs here and we have VO here with respect to ground, and using these two voltage sources we can calculate the voltage at this node by superposition. And what is that node voltage? That is minus Vi with respect to ground. So that gives us one equation like that. So minus Vi is equal to Vs times R2 by R1 plus R2 plus VO times R1 by R1 plus R2. And this part we have got using superposition. Now let us use the fact that VO is AV times Vi. This voltage is AV times Vi. And we also know the frequency dependence for the op amp gain, that is AV of S equal to A0 divided by 1 plus S by omega C. So using these two and putting these back here, we get the following relationship between VO and Vs: minus R2 by R1, 1 divided by all of this. And you are definitely encouraged to derive this equation yourself. Now this term is small because A0 is a large number, 10 raised to 5, and therefore we can ignore this term with respect to this one here. And now we can rewrite the gain of the inverting amplifier, VO by Vs, this one, as minus R2 by R1 times 1 divided by 1 plus S over omega C prime. Now this expression here is the same as this term, and omega C prime is omega C times A0 divided by 1 plus R2 by R1. Now omega C times A0 we have seen before, and that is denoted by omega T, that is the unity gain frequency of the op amp. And for op amp 741, as we have seen earlier, it is 2 pi times 10 raised to 6 radians per second. So now we know the gain of the inverting amplifier as a function of frequency, this expression here, and we can now proceed and plot the gain versus frequency for different values of R2. So here is the gain expression again, VO by Vs minus R2 by R1 times 1 by 1 plus S by omega C prime. So just a single pole, where omega C prime is omega T divided by 1 plus R2 by R1. And omega T is 2 pi times Ft, where Ft is 1 megahertz for the 741 op amp. Alright. So now what we will do is prepare this table and also plot the gain as a function of frequency for various values of R2. For each R2 we will note down the gain, the low frequency gain, which is given by R2 by R1, and also the corner frequency or the 3 dB frequency, which is Fc prime, the same as omega C prime by 2 pi. With R2 equal to 5K, the gain is 5K by 1K or 5, and that is 14 dB. And the corner frequency Fc prime is Ft divided by 1 plus R2 by R1. So that is 1 megahertz divided by 6. That turns out to be 167 kilohertz. And we can see that in this plot here, this is 14 dB. And the intersection of these two asymptotes, this one and this one, should be the corner frequency. So let us see, this is 1 kilohertz, 10 kilohertz, 100 kilohertz, that is 200 kilohertz. So these asymptotes will intersect somewhere between these two, and we see that that is indeed happening. When R2 is increased to 10K, the gain goes up, but Fc prime, the corner frequency, goes down. And now we are in a position to understand why this happens. We have this R2 here in the denominator, and therefore as R2 goes up, Fc prime goes down. And that of course reflects in this graph here. The gain has gone up, and the 3 dB point or the corner frequency has moved from there to there, and so on. As we keep increasing R2, the gain goes on increasing, but Fc prime, the corner frequency, goes on decreasing. So that explains our earlier observation. And the important message to take home from here is that there is a trade-off between gain and bandwidth. We cannot have high gain as well as high corner frequency at the same time.
To summarize, we have looked at amplitude control in sinusoidal oscillators using a gain limiting network. We then looked at the frequency response of an inverting amplifier and explained why the gain drops at high frequencies. In the next class, we will start our discussion of digital circuits. Until then, goodbye.